So we may at last ask the burning question, does this model predict a climate crisis or not? Well, to answer the question, we must check whether the necessary ingredients are there or not. And they are, of course, feedback loops, weak governance, and tipping points. Of course, the question of is this going to cause damage is an easy one. The potential losses of welfare from climate change include extreme atmospheric events like droughts, heat waves, hurricanes, sea level rise, floods, disruption of ecology on land and in the sea, and of course probably of agriculture around the world. It's not easy to estimate the economic impact of such an event, but we try to do so, and the best estimates are generally of a few percentage points of GDP. So, for example, Takakura and co-authors estimate that in year 2100, the climate change would cost around 3.9 points to 8.6 points of global GDP if we stay on current track. So it's actually possible to estimate not only the future damage, but the damage that's occurring right now because of past emissions since the 50s, the 70s, the 80s. How do we do that? Well, we look at insurance markets. So since the 1980s, we see that while insurance costs for most events haven't changed much, insurance claims for hydrological and meteorological events have steadily increased, both in monetary value, so that's on the left, and also as a function of the total number of events, that's on the right. So really, there's no question about the damage. The potential damage is already there. So now the question is, what's the risk for the future? Let's start with positive feedback loops that are actually omnipresent in the climate system. A few prominent examples. So warmer climate means more intense heat waves, which mean drier forests, and drier forests burn more, so they release their CO2 more often, which is, of course, reinforcing climate change. Also, warmer oceans are less good at dissolving and thus trapping CO2. So CO2 stays more in the atmosphere, which traps more heat. Warmer oceans and tundra may release methane, for instance, through methane hydrates. This is not well understood, but if that happened, that would be catastrophic for the climate. Another example is the albedo effect, which may actually be uncertain. So on the one hand, there's the fact that if ice melts in the sea, then instead of being white and reflecting well sun rays, then seawater absorbs most of the heat. On the other hand, more warmer climate means more evaporation, which could potentially form clouds. However, clouds formation is still not extremely well understood. But if that link is confirmed, but then it would be an example of not a positive feedback loop, but actually a negative feedback loop that would actually mitigate climate change. Finally, an economic feedback. So, of course, if there's a warmer climate and less sea ice in the Arctic, it means that potentially we may drill for oil in the Arctic, which would then prolong our use of oil and allow us to release more CO2 in the atmosphere for longer. To have a crisis, we also need bad governance. So we're safe, right? We have climate conferences every few years, so everything is fine. Well, just before looking at the data, let's see that climate is probably one of our most challenging collective action problems yet. Why? Well, because the costs of climate change are local, uneven, they get worse in the future, and of course they are highly uncertain. So both the severity of the problem is uncertain, and also the effectiveness of the proposed solution is also uncertain. So in fact, it's difficult to estimate how much we should sacrifice now and who should be making the sacrifice, rich countries or poor countries or both. And of course, the cost of mitigation are immediate and diffuse in the whole world. So whoever pays, everybody should stop emitting greenhouse gases right now if the world wants a chance to fight it. This graph shows the success of our international efforts at mitigating CO2 over the past 50 years. I have noted 3 major conferences. Now I have been talking for a while, so here's a little quiz for you. According to the press, 2 of these conferences were major successes and 1 was a major disappointment. Which was the major disappointment? Time's up. So it was, of course, the Copenhagen Accord, because there was no consensus and little commitments were made from the actors. But we may console ourselves by looking at the fact that if it's a good or a bad conference, anyways, it doesn't seem to make any difference in terms of CO2 emissions. This map tracks the efforts made by countries to avoid a 2 degrees Celsius warming after the 2016 Paris Agreement. It's by the Climate Action Tracker, a website maintained by scientists. Surprisingly enough, only a few countries that are actually poor are doing enough to avoid the 2 degrees Celsius warming, like Morocco, India, and Gambia. But larger emitters all make insufficient efforts. The biggest emitter is China, where, of course, much needs to be done. However, in September 2020, Xi Jinping has pledged that China would reach peak carbon by 2030 and near zero emissions by 2060. So any news is good news. Of course, this is quite late, but still it's better than nothing. As for other countries like the US, Russia, Saudi Arabia, well, the Climate Action Tracker says that they are barely trying. We may look in more detail at countries for which we have good data. This graph shows estimated emissions after 1995 for the US, Europe, and Russia. At first glance, it's encouraging to see that emissions are mostly stable and even slightly decreasing for Europe and the US. In the US, that was partly due to the decline in coal and the switch to natural gas. Of course, that can't be enough. Also, there was at least one positive outcome of the Great Recession of 2008, a slight dip in emissions. Of course, not much either. So recently, a UN report estimates that global emissions must be reduced by 7.6% per year for the next decade if the world would meet the 1.5 degrees Celsius Paris target. So just to get a visual idea, I have shown what this would look like in dashed line if we started in 2019. So that's quite drastic. The COVID-19 pandemic will certainly help a bit, but probably not enough. So governance doesn't look too encouraging. Let's now turn to the final ingredient in Taylor's model, a tipping point. Now, contrary to ecosystems, it's not that easy to define precise tipping points for the climate. But one thing is for sure, the climate is highly persistent. So carbon dioxide is an oxide, and like all oxides, it's chemically stable. It means that it tends to stay in the atmosphere for decades, if not centuries. For methane, things are a bit better. It tends to go away after roughly 12 years. The problem, though, is that it's 84 times more potent than CO2, and there are lots of methane in the permafrost and in the seabed. And if, for whatever reason, some of that methane was released, then it's essentially like game over for climate change. Even if humans cut emissions to zero, it wouldn't change anything. It wouldn't make a difference. So that's essentially like a tipping point. In an attempt to learn something about persistence of warming, let's look at what we can learn from something from the distant past, more than 55.8 million years ago, actually. It's called the Paleocene-Eocene Thermal Maximum, or PETM. So you see this spike in temperature. They went up by 5 to 8 degrees Celsius in a quote-unquote short time of approximately 20,000 years. And that was accompanied by an emission of CO2 of roughly 0.2 gigatons per year. So the causes are still unclear. Maybe it was a massive release of methane from the seabed, but we're not sure. What was interesting is that climate was totally different. So Greenland and the poles had subtropical climate, for instance. But the interesting aspect is that it took roughly 200,000 years for the atmosphere to absorb all the excess CO2 from that release and for temperatures to go down. So humans now emit roughly 10 gigatons of CO2 per year. So it's 55 times faster than that event. It would still take us roughly 400 years to emit as much. But, 400 years isn't that long to emit a huge quantity of CO2 that could bring us to something quite unknown in terms of climate. And if we do, then it means that we're in there for hundreds of thousands of years. So that's as close as a tipping point as one can imagine. So is a climate crisis likely? Well, to answer that, all these risks should be quantified as much as possible. But the lesson from that paper is that with tipping points and feedback loops, actually chaos and sheer uncertainty will always play a role, and it's going to always be difficult to predict any crisis. With that, Taylor writes, "Do I think a future climate crisis is likely? No, I do not. But then again, no crisis ever is."